This time we'll be looking at level 1 questions about complex impedance, and these get quite a bit trickier than the level 0 ones. Start with the first one. Right, well this is fairly straightforward. Complex impedance at 5 kHz, and it's just two components in series, so the total impedance will be the sum of the two impedances. For the resistor, that's just the value of the resistance, 2. For the inductor, that's going to be the standard inductance impedance formula of J times omega, which is 2 pi 5k here, times the value of the inductance, which here is 33 microhenries. Fine. Next. Here we have a similar idea, but the two components are now in parallel. The standard formula for paralleling components still applies for complex impedances, so we can either do the 1 over Z total equals 1 over Z1 plus 1 over Z2, or the formula Z total equals Z1 times Z2 over Z1 plus Z2. Because the formulas for Z can be a little complicated, this first form of the formula here, where you only have to type in Z1 once, can be a little bit easier to use. So that would be 1 divided by 1 over the impedance of a 330 microhenry inductor at 500 Hz, which would be 2 times pi times 500 times J times 330 microhenries, plus 1 over the impedance of a 2 ohm resistor. And the frequency doesn't matter because the impedance of a 2 ohm resistor is always 2 ohms at all frequencies. Right, that's fine. Next. Another one with two components in parallel, but I'll show you the other way of doing it using the other formula here, using the X and the Y boxes. Well, in X I could put in a formula for the impedance of the capacitor here, which is 1 over J times 2 pi 20 kilohertz, that would be omega, when the frequency is 20 kilohertz, times 6 mu 8 is the capacitance, and that will give me the impedance of that capacitor. Under Y, I'll just have that as 2, that's the impedance of this resistor. So, the total impedance of the two in parallel would be X times Y divided by X plus Y, and let the calculator sort it out. Okay. Right, these are a little bit more interesting. We are given the total impedance, and we're asked what is the missing value, what is the value of this inductor. Several ways to do this one, but I'll show you a graphical way of doing it, because this can be quite useful later on. A real impedance, such as that of the resistor, can be represented by a vector on the real axis here, out there, that point there. 2 has a phase of 0, it's along the real axis. We know the total impedance is 2.17 and it's at 23 degrees. And we also know that the inductor will have an impedance which is perfectly imaginary. Remember, it's J omega L. It's going to be a positive imaginary number. So it would be represented by a complex number along the positive imaginary axis here. Let's say it's there, where this here is J omega L. Right, let's have a look at this. Now, I've got the impedance of the resistor here. I've got the impedance of the inductor adding onto it here. The total impedance is the vector sum of these individual impedances. And we are told that this is 2.13 ohms at an angle of 23 degrees. We don't actually need both pieces of information. We could use the 2.13 And we know that this distance from here to here, that's the magnitude of the impedance of the resistor, is 2. We know that the hypotenuse of this triangle is 2.13. We can work out the length of this side by Pythagoras' theorem. Alternatively, we know that the angle is 23 degrees, and we know that the tangent of 23 degrees will be whatever this distance here, the impedance of the inductor is, divided by 2. Either way will work. I'll just use Pythagoras this time. That would tell me that ZL here, the length of this side of this triangle here, must be the square root of 2.13 squared minus 2 squared. And therefore the impedance of the inductor must be J times that length there. That's the magnitude of the impedance of the inductor. So the total impedance of the inductor is this, and that is equal to J omega L. I also know that omega is the angular frequency corresponding to 2 kilohertz. That's the frequency I was told. So I have that this equals J times 2 pi times 2000 times L. The J's cancel, and I'm just left with L equals the square root of 2.13 squared minus 2 squared divided by 4000 pi. Well, let's give it a try. Square root of 2.13 squared minus 2 squared divided by 4000 times pi. Darn. It's not 2.13, it's 2.17. That was stupid. Great. Okay, next. Complex impedance of this, we've done these before. That would just be a case of taking J times 2 times pi times 100 hertz times 3 henries and putting 1 here, and then it's just x times y divided by x plus y, and that's okay. Now this one is a bit different. It's asking what the frequency must be for this series combination of a resistor and a capacitor to have a total impedance of 2.35 ohms at minus 65 degrees. Well, we can again think about plotting these impedances as complex numbers on an Argand diagram. And if we do that, well, the resistor will have a complex impedance of just 1 ohm. So that would be that point there, just at 1 on the Argand diagram. The capacitor, well, all capacitors have a purely negative imaginary impedance. So it would be somewhere down on the negative side of the imaginary axis here. That's because for a capacitor, the impedance is 1 over J omega C, which is just another way of writing minus J over omega C. It's going to be on this negative imaginary axis. We know that the total impedance has a magnitude of, I'll get it right this time, 2.35 ohms at minus 65 degrees, so that's 65 degrees clockwise from the real axis. I can complete this triangle here. So the total impedance will be 1 plus this distance here, and that would be minus J omega C. So the length of this line here is just going to be 1 over omega C. That's that distance there, because that point there is minus J over omega C. Right. Last time I used Pythagoras to work out the length of this line. This time I'll use the tangent idea. This angle here, 65 degrees, the tangent of that must be the opposite side, this side here, the adjacent side, this side here. Length of this side here is the resistance of the resistor, which is just 1, so we could just write tan of 65 degrees is 1 over omega c. In other words, c times omega is 1 over the tangent of 65 degrees. We know the capacitance. The capacitor is 150 microfarads, so omega is going to be 1 over 150 microfarads times the tangent of 65 degrees. And therefore the frequency will be just 1 over 2 pi times the angular frequency there. 1 over 2 pi times 150 micro, come on, 150 micro times tan 65 degrees. Right, let's give that a try. Back in here, calculator should be able to handle that. 1 divided by 2 times pi times 150 microfarads times the tangent of 65 degrees. Great. Okay, I think that's most of the ideas that you'll need for level 1. Do remember this idea of writing out the impedances on an argon diagram. It can really help when you're combining them in series like this.